Hello and welcome to another WJEC A level physics question. This time it's question 4 from June 2005, PH2, and it's a question about drift velocities and so forth with currents flowing through wires. So first part of the question, we're told the standard formula that links the current in the wire to the drift velocity and other factors, and we're asked to explain the meaning of N in this equation. Well, N stands for the number of free electrons per unit volume, or per meter cubed if you like. Sometimes known as the electron density or the free electron density. It's important here that we have that word free electrons in there, so we're not talking about all of the electrons in a particular wire, it's the number of free electrons per cubic meter. In the next part of the question, we have 4 wires connected to a single wire and then connected to 4 different wires. The cross-sectional areas of the wires in L are the same as the cross-sectional area of this middle wire, and they're all made of the same material, they're all made of copper. We're told that the current in the center wire is 7.6 amps and the drift velocity of those free electrons is 1.4 times 10 to the minus 4 meters per second. And we've got to calculate the value of N for copper. The bit about referring to the data on page 2 goes back to, in this spec, instead of a separate data book, all the data was at the start of the paper. Well, if we rearrange the equation that we were given at the start, the I equals NAVE, we get that N is I over AVE. So let's plug in the values. 7.6 for the current, cross-sectional area 4 times 10 to the minus 6, drift velocity 1.4 times 10 to the minus 4, and E, the electron charge, this is the bit in the data book, 1.6 times 10 to the minus 19 coulombs. If we put that into the calculator, let's see what we get. We get 8.48 times 10 to the 28. And this is very commonly a unit mark question. From the definition, the unit is per meters cubed. Next, we've got to calculate the number of free electrons which passes through any cross-section of the middle wire per second. Well, here we've got to remember that current is the rate of flow of charges, basically how quickly the charges are flowing. The charges are all 1.6 times 10 to the minus 19. So to find our number of free electrons that's flowing per second, all we're going to do is take the current of 7.6 amps and divide it by 1.6 times 10 to the minus 19 coulombs. That will give you basically the total charge divided by the total charge per second divided by the charge of each individual particle, in this case electron, that's flowing through there. So putting those figures into the calculator, we get 4.75 times 10 to the 19. Units would be per second. Next, we've got to calculate the drift velocity of the free electrons in the left-hand wires. So if we look at the left-hand wires, we have the cross-sectional area, but we don't have the current. But a little bit of thought, we should realise that if there's a total current of 7.6 amps in the middle wire, and each of the wires in the section marked L are identical, then the current in each wire will be a quarter of the 7.6 amps. The cross-sectional area is exactly the same. So let's rearrange that drift velocity formula, which will be V equals I over NAE. Well, the N is the same, the A is the same, the E is the same, they're all constants, so the drift velocity is directly proportional to the current. If we have a quarter of the current, the drift velocity will be 4 times smaller. So let's just write a little bit about that. So we'll say that the current in the L wires is a quarter of the 7.6 amps that's in the middle wire. Therefore the drift velocity is, what was it earlier, 1.4 times 10 to the minus 4 divided by 4, which will give us 3.5 times 10 to the minus 5 meters per second. For the last part of the question, we've got to explain why the drift velocity is the same in the right-hand wires as in the middle wires. Well, let's look back at the diagram. The right-hand wires have a quarter of the cross-sectional area compared to the middle wire, and they also have a quarter of the current. So let's put that down. So in R, the current is a quarter of the current in the middle. A is a quarter of the area in the middle. So if we look back at this V equals I over NAE formula, we'll see that we would have a current 4 times smaller on the top, an area 4 times smaller on the bottom. The overall effect of those two will be a cancelling out. So we could express it something like this and show that those quarters cancel. So the basic idea of that question is to realise that even though there's less current in the right-hand wires, there's a less cross-sectional area as well in exactly the same proportion. So thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.